So our next speaker is Violeta Hernández Palacios, who's going to tell us about a Nimble introduction to Nimbers.
Hello. Basically I wanted to talk about one of my pet projects over the past few months. It's something that I've been working on Lean. Maybe you've seen some of my discussions or PRs on it. So basically what I'm trying to do is formalize the theory of Nimbers in Lean 4. And I think the most important question to ask before anything else, here's a little overview, but first I would like to ask, like, why am I even doing this? Like, I would imagine most of you have never heard the name Nimbers. You probably think that I misspelled it or something. So Nimbers are a quirky little thing that Conway introduced in the 70s or so. They're somewhat of an offshoot or like a child or of like ordinal arithmetic and combinatorial game theory. And I think they're a pretty neat theory, but what's the issue? Well, there's a bunch of issues. Like, if you actually read through the literature, I mean, I really don't want to be like talking badly about someone like Conway. I mean, rest in peace. But if you do read his books, you'll find that, I mean, I want to say this as tactfully as possible. Conway was a genius, and because of that, he often didn't really include details that he thought were just like completely obvious. And well, a lot of those details turned out not to be completely obvious. Back in 2022 or so, we formalized one of his proofs that the multiplication of surreal numbers was well defined. It took about, he did it in about half a page. He just kind of hand waved everything to actually formalize it. It took like 600 lines of lean code. We had to like come up with a really weird and niche induction principle on like multisets. We had to like base ourselves on like another paper that described the argument better. And it took like three people. Shout outs to Junyan Xu and Theodore Hua, who I believe were along me some of the people who like contributed to the final proof. And well, it's a bit of a pattern. Conway does these kinds of things a lot of the time. And with a lot of the theories that he developed, there's not a lot of detailed proofs available online because, well, that's another thing. These are kind of niche topics. And well, not only is it hard to actually like find correct proofs if you like look online, but well, in general, if you have something that hasn't been studied all too deeply, then it's easier to have some kind of error slip through the cracks, as actually has happened throughout this project. Um, well, why else would we want to formalize something like this in Lean? Well, I mean, if we're talking about something that has been underexplored, at least in my opinion, having a single resource with all the formalizations for the different theorems is a useful reference for anyone trying to learn about these kinds of things. Nimbers also have a computational aspect to them. Like, Nimbers are ordinal numbers, and well, you can actually talk about natural numbers as Nimbers, and you have operations in Nimber sum, then Nimber multiplication, Nimber division, which the algorithms for them are actually somewhat involved in some cases. So with Lean, one of the things that we could do is formalize those kinds of complex calculations. And I mean, lastly, the main reason I'm doing this is just because it's fun. Let's be honest, that's one of the main drivers to all of us in Lean. It's fun to like formalize new things and find out new mathematics that you weren't really aware of. So with that out of the way, I'm gonna go through a quick overview. I'm gonna briefly just brush on ordinal numbers because at the end of the day, numbers are ordinal numbers, so it's probably important that we'll have like a basic ground knowledge in that. I'm just gonna go through it real quick. I'm gonna talk a bit about impartial games as well, like where this weird concept of Nimbers comes from. Then I'm gonna like describe the basic theory about how Nimbers work, like addition, multiplication, division, roots of polynomials. And then I'm gonna talk about like what I'm actually trying to do in Lean right now. Um, s- I well, since we only have 30 minutes, I'm not sure like how much I'll actually be able to talk about all of these kinds of things, but I'm gonna do my best to like go quick through them. So first of all, let's start about we're talking about ordinal numbers. So the definition that Lean uses for ordinal numbers is that an ordinal is an equivalence class of well orders up to isomorphism. And if you've ever taken a set theory course, then this definition is probably a bit awkward, or like it might ring some alarm bells. Because if you take a set theory course in like university or whatever, you'll usually hear a different definition of ordinal numbers, which is that they're like these kinds of von Neumann sets that are like transitive and have one of like 6 different properties, that they're like well ordered, or that they're like hereditary transitive, or there's a lot of equivalences. But you've probably heard of ordinals as being taught in the lens of CFC sets. And the main reason that we do this is because, well, morally, an ordinal is just supposed to represent like well orders. But in CFC, this definition doesn't quite work out. Like if you actually try to take this equivalence class, if you actually try to take like an equivalence class and you like run through the definition, what you end up with is that an ordinal will have to be a proper class, which is of course unacceptable. That's not something that you can do within CFC. And that's why we end up using von Neumann ordinals. But here in Lean, well, since we have all of these type universes where like one type universe belongs to the other and so on, we can sort of sidestep having to get into the intricacies of like proper class and such. And this definition just kind of works, which is pretty nice, I think. I've actually like previously given a talk about this. I think it might have been Lean Together 2022, where I talked more about like the intricacies of like defining ordinal numbers in Lean and like all the kinds of things that you can do with them. But so right now I'm just gonna like I'm just gonna, well, give the high level details. So we have an ordering relation in ordinals. We define that an ordinal is less than another when one of is an initial segment of the other. By initial segment here, I mean basically a lower set. And well, of course, when I say X is an initial segment of Y, really I'm saying like an element of the equivalence class is an element of the other equivalence class, and this relation can be lifted to the equivalence classes and whatnot. And well, the ordering on ordinal numbers forms a well order, which is well founded as in no infinite decreasing chains. No infinite, yeah, no infinite decreasing sequences, sorry. And also a linear order. And well, every well order is in particular a conditionally complete lattice. As in, for instance, if you haven't heard the term of conditionally complete lattice, basically just think the real numbers. You have a supremum, you have an infimum, as long as your sets are bounded. And well, I even have a little diagram here to like kind of show how the structure of ordinals unfolds. We have 0, 1, 2, 3. All of the natural numbers can be considered as ordinals by just taking like the well orders of that many elements. Then you have the first infinite ordinal, which is omega, the order type of the natural numbers. Then you can just keep going, omega plus 1, omega plus 2, up to omega times 2, then omega times 3, times 4, times 5. You have here omega squared, which is like the order type of pairs of natural numbers under the lexicographic order. And also you can keep going. Like this diagram is very small compared to like how many ordinals or even countable ordinals you can really start to think up. And yeah, here's what I said about proper classes. In in Lean, you don't really have to think about proper classes. Basically, all that happens is that the type of ordinals in a certain universe belongs to the next universe, and everything works fine. Um, so yeah, that was like a brief overview of ordinals. Now I want to talk a bit about games. You know, like combinatorial games. We all love playing those. One of the most basic, well, uh, so there are various types of combinatorial games. You might be familiar with games like chess or tic-tac-toe, where like both players have like a defined set of allowed moves, and these sets are usually different, right? Like in chess, you have the white pieces, the black pieces, and you can't just like grab another player's piece and move it. That's not allowed. In tic-tac-toe, you have like knots and crosses. You can't really like place another player's thing on the board. Like you have to stick to your own pieces. Uh, but there are some games that aren't like this. There are games called impartial games, which are games where both players have the exact same choices. And well, I'm gonna give an example of an impartial game, perhaps the most important example of an impartial game, which is called Nim. And I actually don't know where the name Nims comes from. I think it might have been like some kind of toy company in the 60s who like published the game under that name and then it just kind of stuck. But anyways, Nim is an impartial game that's played with ordinals. You start with a given ordinal like x, and a valid move is to decrease it to any ordinal that's less than x. Both players always have the same valid moves, and whoever is left without valid moves loses, as is the convention in combinatorial game theory. Since ordinals are well ordered, then this is actually a combinatorial game that cannot go forever. And usually think of Nim as, oh, interesting. From the German verb nehmen. I actually didn't know that. So the way that Nim is usually like, the way that you usually like play it, or the way that it's conceptualized, is that you have like this kind of row of counters. Usually you don't have like an ordinal amount, you have just like a natural number. So for instance, you might have 5 counters on the board, and then you can take 2 of them and you're left with 3 of them. Then you can take another one, you're left with 2, and so on. But really, the game can be played with ordinals if you just like keep track of whatever ordinal you're talking about. For instance, here we have a pile of length omega, and the valid move would be to take any amount so that you are left with an ordinal less than omega, which is any natural number. So a valid move here would be to be left with a billion counters, for instance, or 3 counters, or 0 counters actually. Because that's the thing. Nim on its own is a very boring game. If you start with 0 counters, then whoever starts already loses. They have no valid moves. And if you start with some amount that isn't 0, then the first player just takes all of the counters and wins. It's kind of boring, actually. But it can be made quite more interesting when you start to consider multiple Nim heaps side by side. Or in other words, the sum of multiple Nim games. Now, what do I mean by the sum here? Well, in general, if you have 2 combinatorial games, G and H, then the sum of it is the game where both are played side by side. And in each turn, you may even move in one or move in the other, but not both. So for instance, you can consider, here's a fun one. You can consider the sum of sum and checkers. You have these 2 games played with another person, and in your move, you can either perform a move on the chessboard or perform a move on the checkerboard. It's a pretty fun concept, honestly. It would make for quite a chaotic game at night, I think. And in the context of Nim, what this looks like is like having multiple heaps, where you can take an amount of counters from any given heap, but you can only choose one heap. So for instance, we have a configuration here for omega and 5. A valid move would be for a player to take all of the counters in the 4 heap, or maybe leave the omega heap with 7 counters, or that kind of stuff, where you can't take stones from 2 different counters, from 2 different heaps at once. And of course, if you added games like this, if you add impartial games like this, then you're also left with an impartial game because, well, I mean, it's kind of obvious, I think. So here's a fun little fact. The Sprague-Grundy theorem. So to make sense of this theorem, we have to introduce a notion for games that's not really intuitive. It's the game equivalence. And the way that game equivalence works, it's kind of like this. We say that 2 games, G and H, are equivalent whenever, no matter whatever other game we add, then both games end up having the same winning strategies. Or, well, not the same winning strategies, rather the same player wins in both games. Now, a more formal and proper definition of this would be to talk about the ordering of games. This is all in Mathlib, by the way. We do have like the operation, we do have like the pre-order structure in combinatorial games, and equivalence is then just the relation when G is less or equal to H and H is less or equal to G. But to really talk about it from like The most intuitive way to think about game equivalence is basically if you're presented with like either of those two games and you also have like a bunch of other options, then neither of them will be more convenient than the other. That's sort of the way to conceptualize it. Though it's honestly a bit weird and unintuitive, I do admit that. But the important thing here is that any impartial, I misspelled the word game here, I'm sorry. Any impartial game is going to be equivalent to a Nim heap. So if you want to like evaluate, for instance, if you have a given impartial game and you want to figure out who has a winning strategy, then oh yeah, I'm really sorry, I'm going as fast as I can. So if you have a if you want to figure out if you have an impartial game and you want to figure out like who has a winning strategy, there is an algorithm that you can use to basically turn it into a game of Nim, and then we already talked about how Nim is kind of trivial. And well, I'm gonna skip through these details because I am in fact running out of time. Let's go into the meat of this, which is the actual Nimber structure. So what are Nimbers? Nimbers are Nim heaps, basically, and Nim heaps are basically ordinals. So in fact, we can have a very simple definition of Nimbers in Lee, which is just def Nimber equals ordinal. Really easy. Nimbers were a structure first introduced by Conway, who I already mentioned before, in 1976 in the On Numbers and Games. Pretty important paper for like combinatorial game theory as a whole. And well, not only are Nimbers just the same as ordinals, but they also inherit a lot of the same structure. They have the same 0 element, the same 1 element, the same ordering. And well, since we have the same ordering, then we can actually just translate the entire structure of a conditionally complete linear order with a bottom element. So a lot of common structure. What actually differs here are the arithmetical operations. And well, to disambiguate, we're just going to use this notation like asterisk x. If x is an ordinal, then asterisk x will denote the corresponding Nimber. Just so we are always clear on what kind of operations we're using, either ordinal operations or Nimber operations. So what Nimber addition is the most basic operation. And Nimber addition is really just the addition of Nim heaps that I described earlier. Like if you have two different Nim heaps, then by Sprague-Grundy, the game that you get by adding both Nim heaps is going to be equivalent to another game of Nim. Now, you might think that this would require us to develop like the theory of combinatorial games in order to even talk about Nimbers, but fortunately, there's actually a pretty simple characterization of Nimber addition. Well, not really simple, it's somewhat simple. I mean, as simple as this gets. Here, max just means the minimum excluded element, which in other words, just the infimum of the complement of the set. So the Nimber addition between two Nimbers is given by the least Nimber that doesn't appear in any previous a plus y here, or in any previous x plus b. Like if you change either argument to something smaller, the addition is going to be the least value that you hadn't already built. And we can define this in Lean as well. And this is actually in Mathlib now. I added it about 2 months ago. This is a bit of pseudocode. The actual definition is a bit more complicated because of things like getting the termination checker to work and whatever. But it basically boils down to this. And we also have in Nimber, we also have in Lean that in Mathlib that the Nimbers, when given this operation, form a commutative group, an additive commutative group with a 1 element, which pretty neat, I think. And of course, 0 is going to be the identity here. Actually, the result x plus x equals 0 has a very nice interpretation in terms of game theory, which is that if you have like a Nim heap and the same Nim heap, then the second player can win by just mirroring the moves. Like if you move on the first Nim heap, then you do exactly the same thing on the second heap. And if you do that, then the second player wins. But the only Nim heap in which the second player wins is in the 0 Nim heap. So you have this equivalence, which is pretty neat, I think. And you can even have a more explicit characterization. Basically, Nimber addition just corresponds to like I mean, I have this like I have here like the more formal conditions, but basically Nimber addition is just the XOR, the binary XOR operation. On natural numbers, then this behaves like you would expect. On general ordinals, then by what I mean by XOR is going to be in terms of the binary Cantor normal form. Like you may know that every ordinal has a sort of base X expansion, except that instead of using bases, use like general ordinals. And what that basically means is that you can like kind of write an ordinal in binary, and then Nimber addition just corresponds to the XOR operation on said binary expansions. So here's an addition table for the first few natural numbers. Yeah, you can see that in this case, it's just the XOR operation, nothing really fancy going on here. Now, Nimber multiplication, and this is where things really start to get weird. Because as far as we know, and I mean, I would classify this as an open problem, but I think that's up to interpretation. As far as we know, we don't really have any known connection between Nimber multiplication and the actual game of Nim. Like, Nimber addition is very clearly inspired by the game of Nim. Nimber multiplication is where things start to get a bit weird. It's more like you're generalizing the definitions based on vibes, and it's somehow still giving things that make sense. Because you can think of Nim addition as sort of giving the least answer that guarantees injectivity in both arguments. Nim multiplication is sort of the least answer that guarantees that you have a domain. Precisely, you have like x minus a times y minus b, it's not equal to 0 whenever x is not equal to a and y is not equal to b. And that gives you this. And it's a very weird operation. It's much weirder than Nimber addition. And it's much less understood. But here we have again a lean pseudocode kind of thing, and we can prove that this is a commutative ring and that it's a domain with again the one identity. So we do have some characterizations for Nimber multiplication. This actually isn't in math a little bit. I'm still trying to figure out how to like get it into it. But we do have this very weird characterization. Basically, you characterize Nimber multiplication in terms of Fermat powers, and you get these pretty weird results. On natural numbers, these two results, alongside all of the properties of rings, are actually enough to completely characterize Nimber multiplication. You can even come up with an actual algorithm. That's another thing on my to-do list. But unfortunately, these theorems don't generalize to infinite ordinals, and in fact, we don't even have a full characterization of Nimber multiplication yet, even below this value, which later on you'll see why this value is sort of relevant to all of this. And here's a table which you can see is actually just a mess. I mean, you can kind of try to stare at it and try to find some patterns, but there's not a lot to it. I hear that there's some connection to Walsh permutations, but I don't really know much about all of those details. And not only can you multiply Nimbers, but you can actually take division of Nimbers. And this one is even weirder because we don't actually have like a characterization or an algorithm to even calculate it. We do have like this theorem which allows us to define it. If x is not equal to 0, then you can characterize the inverse as the minimum excluded value of the smallest set that contains 0 and contains all of these values. So very weird definition, and in fact you can see that we have to define it through mutual induction. So thanks to Leo for making that work in Lean 4. So yeah, we have like this auxiliary inverse, which is the minimum excluded value of this auxiliary set. And then this auxiliary set is defined as the intersection of all the sets to satisfy these conditions. And then the actual inverse just like corrects the value in 0 because Lean stuff. And once we have all of this, we can actually prove that Nimbers are a field. This is almost in MATLAB. It's like, it's already been reviewed. It hasn't been completely merged yet. And, well, yeah, that of course means that the Nimbers was then to the n form a finite field. The finite Nimbers are the direct limit of these fields, though we don't really know which infinite Nimbers form a field. And here's a division table. You'll see that I have a bunch of zeros here and here because Lean conventions. Again, this is a complete mess. And here's the really weird part, Nimber polynomials. The definite Nimbers are not algebraically complete. Like that's something you can actually prove. For instance, the smallest root of this polynomial, x to the cube minus 2, is omega, which is weird, I think. But amazingly, if you take all of the Nimbers out there, you do have an algebraically complete field. And that's a result that I've been working on getting to MathLib. I mean, I've gotten a bit sidetracked with other projects related to ordinals, but this is mostly been proven. We've proven most of the auxiliary lemmas. And well, when I say we, I mean me and Daniel Weber, which has actually helped me a lot throughout this project. And well, that's something that we're currently working on to like get formalized. Here's a few open problems because we really don't know a lot of things about Nimbers. And so yeah, here's like kind of the to-do list with with formalizing all of this into lean. I do wish I had a bit more time to discuss some of these things, particularly the simplicity theorems. They're pretty interesting. They have actually been sort of relevant to this whole conversation about like unbundled groups and all of that, because the simplicity theorems depend on these sorts of notions of like talking about a specific set being a group or a specific set being a ring, that kind of stuff. But well, I think I'm almost out of time right now, so I think I'm just gonna like finish up all of this fast. And well, these are basically the things that I would like to get into MATLAB, you know, the simplicity theorems, which kind of are the best understanding we currently have of the structure of multiplication and division and all of that on Nimbers. The result on algebraic completion, on algebraic completeness, which is very related to it. And of course, algebraic completeness below this ordinal in particular, which is the least ordinal, which is algebraically complete. That would be a really cool project to show, I think. And it would actually require a bunch of field machinery. So having the whole power of MATLAB behind it would be pretty cool, I think. And of course, it would be nice to be able to have like computable operations on the finite numbers, you know, like you just eval a name product and it just gives you the answer. That would be really nice if we could do that. So here's a bunch of bibliography. These are like some of the sources that I could find on this topic of Nimbers. If anyone of you is interested in like investigating on that kind of stuff further. And that's basically it.